Hi, I'm Tyler Fultz. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry, from engineering to operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Today we're going to be looking at a video by NileRed on making uranium glass. I've never even seen or held uranium glass before. Worked with uranium a lot as far as a nuclear fuel, but never in this capacity. Let's check it out.
Last year was the first time that I heard about uranium glass, and I thought that it was some marketing thing or something, but it's actually real. I mean, it's not glass made entirely out of uranium, but it is glass with uranium in it.
Sure.
This got me really interested in it, and I decided to buy some, and I got this cup of it off eBay. Pure uranium glass is normally yellow, but this one is green, and I think it's because they put some iron into it.
Glows in the dark.
Regardless of that, though, that's not really what makes uranium glass special, and it's what it looks like under a black light.
Yeah.
The uranium in it fluoresces, and it makes this really nice green color. The actual amount of uranium in it, though, is quite small, so the glass itself is only minorly radioactive.
That's another thing. Okay, I can see where people getting more of the green glowy uranium from. Maybe it's like glass. I saw salts in another video I reacted to by Styropyro. So yeah, it's when you do these little fun things, which oddly enough have nothing to do with the nuclear industry. It's kind of funny.
General glassware and cups like this were super popular in the late 1800s and the early 1900s. However, during World War II, the government started confiscating all the uranium and diverting it to nuclear research. Yeah. This kind of killed the entire industry for uranium glass until the late 50s, when some restrictions on uranium were lifted.
I had no idea people did that much with uranium before World War II. That's interesting. Other than like experiments, I didn't know there was a consumer goods industry associated with uranium. That's interesting.
A few companies started making it again, but at that point, the health effects of radiation were a lot more well known. And also, after the nuclear bombs, the public perception of uranium wasn't exactly great. Nowadays, there are...
He says that it's like, wasn't great back then, but yeah, imagine it's even crazier now, as in you have people thinking that the water vapor coming out of cooling towers of a nuclear plant's radioactive. He's right, but it's even crazier now.
Apparently still a few companies that make it, but I wasn't able to find any of it for sale. As far as I know, if you want to get some uranium glass, you really can only buy the old stuff. I found this all really interesting, and I've been wanting to work with uranium for a while, so I decided to make some uranium glass.
Cool.
My original plan was to buy some uranium ore and then refine it and use that purified uranium to put into some glass. However, I learned from Cody over at Cody's lab that the government doesn't really like it when you show how to refine uranium on the internet. Instead, I had to start with an already purified source, and I was able to find some depleted uranium. This means that it's missing the isotope to do things like generate nuclear power or make nuclear weapons.
I love this pros-cons list. So pros, easier to get. Cons, no nuclear energy. I agree, that's a con. Can't make bombs. That's a con? I love this. But depleted uranium is actually used in weapons, not nuclear weapons, but the A-10 Warthog, its ammunition that it uses to split tanks in half involves depleted uranium. Armor on an Abrams tank involves depleted uranium. So you can't make nuclear weapons, but I guess you could make nuclear, weapons.
However, it's still good for making glass. Uranyl nitrate is the nitrate salt of uranium, and when it's pure, it can form these nice yellow crystals.
Whoa, that's cool.
Besides just kind of looking pretty, though, it seems relatively mundane, and that's something that I've always found interesting about radiation.
Yeah, uranium nitrate, again, never really worked with it. Mainly uranium oxide, which is just a black little pellet, and fresh uranium, which is just a silvery metal. So it's interesting that the uranium used in nuclear is actually more mundane than what this guy's using.
As this uranyl nitrate just sits there, it's shooting off thousands of extremely small particles, but they're way too small to see or to feel. So,
an alpha particle is a helium nucleus. So, yeah, you ain't going to see that.
There's no way to naturally perceive that it's there, and this was one of the biggest reasons why it took so long to discover radiation. To know that it's there, it has to be detected using some sort of instrument or setup, and over the years, many different methods have been developed.
Cloud chambers.
Nowadays, one of the easiest ways is to just use a Geiger counter, but before starting this project, I didn't have one. However, when working with something radioactive like uranium, it's pretty much absolutely necessary. So I looked around online, and I ended up getting this one off Amazon, which wasn't very expensive, but it was supposed to be decent.
Yeah, Geiger counters are very inexpensive, probably one of the least expensive and most user-friendly radiation counters detectors to use.
I turned it on and I let it stabilize for a minute, and I saw that the natural background radiation was about 15 CPM. CPM stands for counts per minute, and it's a reading of how many radioactive particles it detects over a minute.
Specifically, how many ionizations it detects. Note that stuff like sunlight, which is technically a form of radiation, isn't going to be detected, but strictly ionization, so natural ionizing radiation is what he's looking at.
Radiation exists everywhere in the environment, and you're always being bombarded by it naturally, and this reading of 15 CPM is actually quite low. Now, it was time to test it with the uranium, so I just put it next to it. There was clearly an effect, and this Geiger counter was going to be more than usable for this project, but it unfortunately wasn't going to be super accurate.
So part of it is alpha particles have a very short range, and even that little casing of that little vial he has there, that's going to stop some of those alpha particles. So this thing's actually reading pretty low.
Because most of the radiation that's let off by uranium is in the form of something called alpha particles, and this counter's not even able to detect them. It's only able to pick up the beta and the gamma rays that it's letting off, which are significantly less than the alpha. Despite this though, it's still going to be really useful because I don't actually need a super accurate reading, I just have to know whether or not it's there.
That is the exact purpose of a Geiger or Geiger-Müller counter. It's just to tell you if radiation is there. We mainly use it to scan for contamination, not discriminate between what type of radiation you have. You can see why. So for Geiger-Müller detectors, the voltage is significantly high, and the device is simple enough that it's not going to distinguish between what type of radiation there are, whether it's alphas, betas, gammas, and regardless of what energy level they are, it's all going to do the same thing. One bit of incident radiation is going to ionize the entire chamber. Now, for different types of counters, like a proportional counter, like a gas-filled ionization chamber or something, it can discriminate between what type of radiation you have. You can even graph it to see where the peaks are and how much of it's alpha, how much of it's beta, if you have a mixed source and you're trying to figure out what it is. But he doesn't need that for what he's doing. You're just trying to find out what's radioactive and what's not.
Now, before getting started, I just wanted to try one other thing. Uranyl nitrate was supposed to be fluorescent under UV, so I put some on a dish, turned off the lights, and shot it with my black light. And well, it was definitely fluorescent. This made me think that maybe to make the uranium glass, I could just directly throw the uranyl nitrate into some molten glass. However, when I looked it up, it didn't seem like that was the case.
So the main hazard associated with handling uranium itself is internal dose. So don't eat it, don't inhale it. It'd probably be good for him to have a fume hood nearby just in case. I don't know if he's wearing a face mask or not, but you can touch it and be fine. You can put it won't penetrate the skin. And like you said, betas and gammas are trace. They're not even much above background radiation at this point.
I mean, I could barely find anything about making uranium glass in general, but out of all the info that I did find, it always mentioned using something called sodium diuranate. Based on this, and considering the fact that I'd never made uranium glass before, I figured that it was probably best for me to use that as well. Now, though, this meant that the project was going to be a bit more fun because I'd have to do some uranium chemistry to convert the uranyl nitrate into the sodium diuranate. To get this started, I had to add the uranyl nitrate to a beaker, and normally, I would have just quickly weighed it out on some paper and then dumped it in. However, this time, I was working with a uranium compound, so I had to be a lot more careful. This is because the dust that it could let off is not only radioactive, it's also toxic, and it can lead to heavy metal poisoning.
That's true.
So, to be as safe as possible, I carefully weighed everything directly in the beaker, and in total, I used about 15 grams.
That's one instance, and this was actually happened during the some of the Chernobyl cleanup, was when they used lead because lead is stable, not radioactive, to extinguish some of the fires mixed with sand and boron and a bunch of other materials. I talk a little bit more about that in my review of the Chernobyl series. But the lead itself can melt and even boil when it gets that hot, and it can become an airborne hazard. And basically, that thing turned out to be just as deadly as the radiation from the accident, just because of all the lead poisoning. And most radionuclides eventually, of the heavy stuff like uranium, eventually decay to lead over a very, very long period of time. But just because it decays to lead doesn't mean it's doesn't have the potential to be hazardous when it's lead.
Then on top of this, I dropped in a magnetic stir bar and I poured in some water, which should have been enough to dissolve all of the uranyl nitrate. I turned on the stirring and I waited for it all to disappear, but unfortunately, it ended up staying a little bit cloudy.
Wow, okay.
I tried adding some more water just in case there wasn't enough, but it didn't seem to do very much. This was unfortunate because it now meant that I had to clean things up a bit, and I didn't really want to have to work with a solution of uranium.
Yeah.
Thankfully, however, cleaning it up wasn't exactly going to be super difficult, and I just had to do a quick filtration. I did this by passing it through some cotton and some sea light, which is kind of like superfine sand. The stuff that initially passes through tends to still be a bit cloudy, so I let it run for a bit, and then I swapped it out for a new beaker and put the other stuff through it again.
Okay.
After this, it was perfectly nice and clear, but there was still a bunch of uranium solution all over the funnel and in the cotton and sea light, so I washed it out with a bit of water. When all the water had eventually passed through, I took away the funnel, and the solution was pretty much good to go. Now,
so on the subject of nuclear waste, if this we've never done this sort of work in a nuclear power plant, but if we did, anything with uranium in it, we're going to be conservative and treat that as nuclear waste. This would be low-level waste and would just involve cleaning. But people talk about nuclear waste and how difficult it is to dispose. Well over 95% even is easy to clean. In some bits, you need to wait for it to decay away. Not the case with uranium. The little bits on his funnel, if he can't get it off, would technically be considered nuclear waste, which is interesting.
Convert this to the sodium diuranate, I had to react it with something called sodium hydroxide. This is also known as lye, and it's often sold as drain cleaner, and that's where I get all mine from. For this reaction, it also all had to be dissolved into water, but the exact concentration of it didn't really matter. I figured that something around 30% by weight would probably be good, so I measured out about 70 mils of water and dumped in roughly 30 grams.
Sodium hydroxide is, at the nuclear plant, we use it just for pH control. It's caustic. No, not really any different than pH control in any big industrial place that has a lot of pipes that you have to eventually worry about corrosion, pH, conductivity, things of that nature. And this is just one of the chemicals that you use to control the water chemistry. It's just water-related stuff.
It all dissolves relatively easily into water, but it also generates a lot of heat, so in the end, the solution is usually pretty hot. However, I wanted it to be closer to room temperature, or maybe just slightly warm, so I put it in the fridge to cool it down. When I felt that it was good, I took it out of the fridge and I started slowly adding it to the uranyl nitrate. Almost immediately, it started forming these weird, solid, kind of donut-looking things, and this was all sodium diuranate. The reason this happened was because unlike the uranyl nitrate and the sodium hydroxide, the sodium diuranate is practically insoluble in water, so the moment that it formed, it separated out.
Cool.
What I had to do now was basically just keep adding the sodium hydroxide until it stopped making the diuranate. At this point, it was still pretty simple because the solution was nice and clear and it was really obvious to see. However, I eventually started stirring it and the whole thing got a bit murky, so I couldn't just rely on looking at it. Instead, to know when it was done, I had to keep testing the pH. I did this just using some cheap pH papers, and I kept adding the hydroxide until it turned blue, which told me that the pH was about 10. After this, I just let it sit there for a bit to make sure that it all fully reacted, and then I filtered it off. I just did this by pouring it through a simple coffee filter, and when most of the water had passed through, I washed it a few times with distilled water. I then let it sit there until all that water passed through as well, and now I had some relatively clean sodium diuranate. It was all still wet and goopy though, and I'd have to dry it out, but it was going to take forever just sitting here in the strainer. With other chemicals, I'd usually just set up a fan on the side to help speed things up, but that would probably end up shooting a small amount of dust into the air, and I didn't really feel comfortable doing that with uranium.
No.
So instead, I carefully took out the coffee filter and I put it in a bowl and I pulled a vacuum on it. Under a vacuum, water vaporizes a lot more, and this makes it dry a lot faster. In a closed space though, like in this vacuum chamber, there's nowhere for the water vapor to go. So to fix this problem,
no risk
I
of
included a bunch of drying salt at the bottom, which would constantly pick up the water vapor. I pulled it out about 5 hours later, and it was mostly dry. I purposely didn't let it dry completely because I wanted to avoid as much dust as I could. By keeping it slightly wet and a bit pasty, I was able to pretty safely scrape it all off without making any death clouds. Also, besides the safety issue, I was worried that if I let it dry completely, that it would just stick to the paper and become impossible to separate. I was able to get almost all of it and put it into a small bottle, but there was still some stuck to the paper. Getting this last bit was a lot sloppier than I wanted it to be, but I didn't really have any other alternative. I just did my best to scrape it all off, and then everything that even remotely came into contact with the uranium was put into a special waste container. Everything that I took off was transferred to the same small bottle, and I did it as carefully as I could, but it was still a bit messy. There was a bit of uranium that managed to get on the outside of the bottle, and I of course had to clean that up. And I did this by just wiping it down a few times with some wet paper towel. Now, with all the uranium safely in the bottle, and none of it on the outside to poison me when I touched it, I was ready to finish drying it. To do this, I put it into the same vacuum chamber that I used earlier, and I pulled a really strong vacuum on it. I wanted it to be as absolutely dry as possible, so I left it in there for 3 or 4 days. So I came back to it a few days later, repressurized the chamber and took it out, and well, it worked. It was really dry.
Yeah.
When it's dry like this, though, it has a tendency to give off dust and powder, which is obviously really horrible to breathe in. This was why I only dried it completely in the final container that I was storing it in, so I wouldn't have to move it around or handle it.
That's smart.
I went ahead and weighed what I had here, and it came out to be 9 grams, which was about what I expected. Just for fun, I decided to test it with the Geiger counter, and you can see that the glass was able to block most of the radiation. The reading that it had was only barely above the normal background level, but that totally changed when I moved it over the top.
Yes. Oh yeah.
The reason this happened was that most of the radiation that was being let off here was in the form of alpha and beta particles, and they just couldn't make it through the glass.
Beta would be stopped by the glass. Something about this with the thickness of your credit card could probably stop a beta. Could stop normal beta particles unless you threw them through a particle accelerator or something.
As I mentioned before though, this counter isn't able to pick up alpha particles in general, so what I was seeing here was probably mostly from beta particles. Now one other thing that I wanted to try was to shoot UV on it, and I was surprised that it didn't fluoresce. I mean, maybe it was fluorescing and it was just super weak, but as far as I could tell, it was pretty dead. I thought this was really interesting because logically, you'd assume that if you wanted to make glass fluoresce, you'd put something fluorescent in it. However, I guess that just isn't the case, and glass chemistry is a bit more complicated than I thought. But anyway, now that I had the sodium diuranate, I could start trying to make the glass. However, I'd never made glass before, so I kind of had no idea how to do it. I looked around online, and one of the best things that I found was a video by Ben, who runs the channel Applied Science. He gave a lot of good details and tips, and almost everything that I'll be doing here is based on stuff that I learned from him. I also got a few tips from Andy, who runs the channel called How to Make Everything. When it comes to making glass, it's not super straightforward, and there are a lot of different ingredients that can be used. For beginners though, Ben just recommended to use a mixture of 3 different things.
I've never made glass.
Sodium carbonate, and boric acid. So that's what I went with, and all these ingredients were really easy to get, and I just ordered them all from Amazon.
Now, boric acid is interesting because we actually use that in the pressurized water reactor that I worked at. Think of it as a liquid version of control rods because it contains boron, which has a high absorption rate of neutrons, higher than that of uranium, so it stops the fission reaction. So, another way you can borate, which is adding boric acid to the reactor in order to lower reactor power, or you can dilute it, just add more pure water to the reactor, and that will raise reactor power. That's actually how, in a pressurized water reactor, we say maintain temperature colloquially in operations, but temperature and power still kind of still follow. But because you're really, what happens is you're using up more of the fuel and then you dilute to compensate. Like, for instance, at the beginning of life, at the pressurized water reactor I worked at, the boric acid concentration is about 1,400 parts per million. And then at the end of life, right before you need to shut down and refuel because you used up all the fuel, the boric acid concentration is less than 30 parts per million. It's another way to control reactor power in addition to control rods. And one of the reasons why you have multiple methods of doing so is redundancy. So, in case you have one issue or one of your systems doesn't work, you have another way to do it. And 2, about power peaking. They change the power distribution in different parts of the core, the boric acid versus the control rods. So it's nice to have both for just a more uniformly distributed power level within a nuclear reactor.
I then got a jar, added 60 grams of each, and shook it up to mix it a bit. Like this, it would probably work to make glass, but in my opinion, the powder was still too chunky. So to fix this, I put it all into a blender, and I ran it for a few minutes. This apparently worked pretty well, and after this, it was a super fine powder, and it kind of looked like flour. This was definitely way better than before, and I hoped that it would give me a better quality glass. Before adding any uranium to it though, it was a good idea to test it to make sure that it worked. I had also never made glass before, and it was probably a good idea to get at least some experience making it before trying it with uranium in it. The general idea behind making glass was very simple, and all I had to do was melt this powder. So, I added a bunch of it to this dish that I had, which was normally used to melt things like gold, and I put it into a small furnace. By the fact that it was glowing orange, it was obviously pretty hot, and I'd set it to around 1100 C. I wasn't completely sure that this would be hot enough to melt it, but when I checked on it a few minutes later, it looked like it was working. And now, because there was more space in the dish, I decided to add some more glass. At this high temperature, the sodium carbonate was mostly just melting.
To give you a sense, 1100 C, you're getting into nuclear fuel temperatures. Normal nuclear fuel temperatures.
But the boric acid was breaking down into boron trioxide and water vapor. This caused it to bubble a bit, and you can see this if you look really closely. The main purpose of these chemicals, though, was that they both have much lower melting points than silica, and they help lower the overall melting point of the mixture. Pure silica only starts melting around 1700 C, but at that point, it's still way too thick to work with, and you have to get it well over 2000.
One thing is during the Manhattan Project at the Trinity atomic detonation, since you're in a desert, all that silica in the sand, a lot of that turned into glass because of the extremely high temperatures of the atomic bomb.
The temperature this high is just very hard in general, and because of this, additives are almost always included to lower the melting point. In my case, because I used boron trioxide, the final result would be some sort of borosilicate glass. In general, borosilicate glass is a lot less sensitive to big changes in temperature, and I hoped that this would help prevent the glass from cracking as it cooled down. But anyway, I let it sit like this for about 30 minutes, and I waited for it to completely liquefy. When it eventually looked like it was about ready, I used a blowtorch to preheat a graphite square. Then, I carefully got the dish from the furnace, and I poured out all the glass. I let it cool over the next 15 or 20 minutes, and it looked pretty decent. It looked like just a regular piece of glass, and I was actually pretty proud of it. I really thought that it would crack, but apparently it didn't, and I was still a bit skeptical of it. So I left it overnight to see if anything would change, and by the next day, it was still totally fine.
That's cool.
As far as I could tell, this glass mixture worked pretty well, and the process seemed to be relatively simple. After doing it just once, I was definitely by no means a pro at making glass, but I felt that I was ready to get the uranium involved. To do this, I just had to add some uranium to the glass mix, but it was still a bit too chunky. If I added it like this, it wouldn't mix in properly, and it would make some really uneven glass.
Don't inhale the powder.
So far, I had really done my best to avoid working with any powdered uranium, but unfortunately, I didn't really have a choice here. I just did my best to grind it very carefully, and to try to make as little dust as possible.
Orange.
When I was done, I put it all back into the bottle, and everything that came into contact with the uranium was put into my waste container. Now, to actually add it to the glass mix, the amount of uranium that I needed was super small. However, I didn't know exactly how much I had to add because from what I found online, some recipes use as low as 0.1% uranium.
I like those, uranium recipes.
This concentration was all done by weight, and I decided to go with a moderate 0.25%.
Yeah.
I figured that this way, if the final glass didn't glow well, I could just add some more. At 0.25% though, barely any was needed, and for what I had here, I only had to add 0.4 grams. To mix it in, I shook it around for several minutes, and when I was done, it looked the same as it was before the uranium. As far as I could tell, it was still really white, and I guess there just wasn't enough of it to noticeably change the color. The dish from before was already in the furnace, and I started loading it up with some spoonfuls. I waited for this all to melt, and then I added some more.
Recipes, spoons involving uranium.
Also, as a
never had that
safety,
experience.
This was all being done in my fume hood, just in case it let off any uranium fumes. In reality, there probably wasn't much or any of it, but it was obviously something that I had to be very careful with. When I checked on it and it looked ready, I preheated that graphite block again. Then I took out the dish and I poured out what was hopefully uranium glass. While it was still red hot, it was hard to tell, but as it cooled, it was definitely colored this time.
It
also shrank a bit, and when I felt that it was solid enough to move, I picked it up and put it on some glass insulation. With a white background, the color was a lot easier to see, and it was a really nice and bright yellow. This was exactly what I was hoping it would look like, and so far, things seem to be going pretty well. Now the next thing to do was to test and see if it was fluorescent. So I got out my UV lamp, turned it on, and, it was kind of working. The glass was definitely a bit green, but it wasn't very impressive to say the least. My first assumption from this was that 0.25% just wasn't enough uranium. However, then I thought, maybe it was just still too hot, and I had to wait for it to cool down. So I decided to have some patience and to test it again a few minutes later. This time, it still wasn't amazing, but it was for sure better than before. I then let it cool completely down to room temperature before testing again, and this time, it worked really well. The
There's that green glowy uranium that a lot of people think of when they think of uranium.
I guess I wasn't going to have to add any extra. There was still some glass left in the dish, so I poured it out as well, and I made another little flat glass thing. This one also worked really well once it was at room temperature.
That is so cool.
And it glowed nicely under UV.
I'm really appreciating him showing us all the steps to make this uranium glass and this stereotypical view of uranium, and there's quite a bit involved. Taking him, I lost count at the time, but it's taken him over a week at this point, because I know he said that one step involving drawing a vacuum and leaving it under there for several days. So yeah, it's pretty involved.
After making these, it was getting late.
Not as involved as enriching uranium, but still.
And come back in the morning. Unfortunately, though, when I checked on the glass, one of them had spontaneously broken. These pieces were a lot bigger than that first test run, and it was looking like this might cause some problems. One of them was still okay, though, and I thought that maybe only one of them breaking was just some bad luck. Then, almost as though it somehow knew what I was thinking, it responded by splitting in half right when it was sitting in front of me. This was completely random, so I unfortunately didn't get it on camera, but this made it clear to me that there was an issue. This was happening because I had cooled down the glass quickly and unevenly, and it had caused a lot of internal stress. What I thought might work to fix this was to just insulate the glass and have it cool down really slowly. The final result would still be under high stress, but I was hoping that it would lower it enough just so that it would stop spontaneously falling apart. For this one, I also decided to try making it a lot bigger, and I loaded up way more glass. I then poured it all out, and the moment that it looked solid enough, I put it between some insulation. After that, I moved it to one of my benches to cool, and it initially seemed to be working well. However, a few hours later, I heard the sound of breaking glass, and this was what I came back to. A lot of stress had clearly built up, and it was apparently enough to shoot some of it a couple inches. The pieces that survived didn't seem to be too fragile, at least when I was hitting them. However, shocking them with heat probably would have caused them to pop.
Breaks when you walk away.
I decided to try breaking a piece of it with pliers, and it was surprisingly difficult. The moment that it did break, though, it just exploded from all that internal stress.
Hope you got your safety glasses on,
buddy. I thought
this
was really cool, but what I wasn't a fan of was all the powdered uranium glass dust that was flying everywhere.
Yeah, ooh, the dust, yep.
After doing this, I realized my only real option was to anneal it. To do this, I'd have to hold the glass at around 450 C for several hours. At this temperature, the glass is solid, but it's still liquid enough that its atoms are able to move around. This happens really slowly, which is why it takes several hours, but it lets them move to new positions and reduce the overall internal stress. This is the proper way to do things, and it's what I ideally would have done before, but I was trying to avoid it because I only had one furnace. This makes it much more difficult and slow to do things, but I figured I would try it out. I still really wanted to make a big disc of it, so I melted the rest of the powder that I had, and I poured out another one. Then, as it was cooling, I quickly changed the furnace temperature to 450 C, and I put it in. To anneal this, it would take at least several hours, and I was planning to leave it overnight. In the meantime, I collected all the broken glass that I had, and because now I didn't have a furnace, I melted it with a torch. Now what I wanted to try here was to do some glass blowing with it, but I had no idea what I was doing, and it was a total failure. Instead, I just made several beads that I thought were
like this guy's determination, though.
I really do. Without annealing them. However, at the last minute, I got the genius idea to anneal them just in case. I knew it was a bad idea to open the furnace, but I did it anyway, and it was, well, a bad idea. I tried to put it in quickly, but where the beaker touched the disc, it started forming a crack. I then tried to move it around to get a better look at it, and cracks formed everywhere that I touched. I actually thought that this was pretty cool, but now I was worried that it would just end up exploding again. So I took it out, and I blasted it with a torch to heat it up again and to melt the surface. This way, I was hoping that even if there were cracks, if I sealed the top, it could prevent it from falling apart. After this, I put it back into the furnace, and I let everything anneal overnight. The next day, I was worried that I'd open it up and just see a disaster. I was initially a bit disappointed that the big piece got so cracked, but I actually ended up liking it. I think having it like this made it a bit more interesting.
That's so cool.
I think the small beads that I made also turned out really well, and none of them were cracked or falling apart.
Nice.
The question that I had now, though,
make uranium marbles.
How radioactive were these pieces of glass? Considering the amount of uranium that I put into it, it was definitely quite low, but I still wanted to test it. The Geiger counter that I had, though, wasn't the best for this, and I decided to invest in a better one. This one is much more sensitive and has a bigger detection area.
Wow,
and it can also detect alpha particles. To test it out, I did...
Interesting. That's... okay. Those are more expensive. Wow.
The biggest piece, and with a uranium concentration of only 0.25%, I assumed that the reading would be really low. However, it was more than what I got with the pure uranyl nitrate because it was now actually seeing the alpha particles. The detector also had a totally different shape and a much larger surface area, which let it pick up many more particles. As a unit, CPM only shows the strict number of particles that it detects, and it doesn't differentiate between things like alpha, beta, or gamma.
Yep.
This is important, though, in trying to judge how dangerous a radioactive source is, because they aren't all equal. For this reason, it's sometimes better to go with a different unit, like sieverts, which will take this into account.
That's good. This is a pretty high-end Geiger counter. Most of them that do the conversion aren't pure Geiger counter. It would have to discriminate between the two, take the energy into account as well, and do a little calculation. This is beyond the level of a pure Geiger counter.
Sieverts per hour, this gave a reading of about 5.5.
That's actually more than I figured. 5 microsieverts per hour is comparable to that of a dental X-ray, or eating about 50 bananas.
And according to this, which I got from the Canadian Nuclear Association, it means that if you held your cheek against it, it would be like getting a dental X-ray every 2 hours. Now for one of the beads, I got that it was only about 1.3 microsieverts per hour, and this was just because it was a lot smaller. In either case, though, at this level of radiation, this glass is generally safe to have around and to occasionally handle. However, it would be a very bad idea to fill your pockets with them or something and to carry it around all the time. It might be okay to occasionally wear it as a necklace or something for a short period of time, but I don't think it's the greatest idea.
Nah. The philosophy of health physics, radiation protection, try to keep radiation dose as low as reasonably achievable. And I can totally understand the reason for not wanting to have it on your purse. That was really cool. I've, like I said, never done anything with uranium glass. It was cool to see that green glow in something realistic. And again, it was actually more radioactive than I thought it was, which is just fascinating that you can make something like that. Still, I knew it was still going to be in a relatively safe level. It was really cool to see someone go through all the processes and see how laborious it is to do something like that. It's very, very fascinating. This is going to be how he disposed of the waste. Let's check it out.
A few days ago, I posted a video about uranium glass on the main channel, and I originally wasn't planning to do a cleanup video for it, because I honestly didn't think that there was much to show. However, there have been a lot of comments asking for one, so I decided to do it anyway. Most of the mess in this project came from when I made the sodium diuranate. It left me with a bunch of stuff contaminated with uranium, as well as dirty paper towels and gloves. In this shot, it looks like there's only 2 pairs of gloves or something, but off screen, I had another bag full of them.
So let's talk a little bit about nuclear waste to start with. 3%, and what most people think of the waste, is the high-level elements that are fission products that are in spent fuel assemblies, and that accounts for almost all of the radioactivity associated with it, just in terms of Curies, how radioactive the stuff is. Now, all of that is stored in spent fuel pools or in dry cask storage. And those dry cast canisters are massively resistant to even direct missile strikes, severe weather, super, super secure. And those are stored on pads outside of nuclear power plants. So he doesn't have anything like that. And then you have intermediate level waste, which is where you have like some filters and some bits and pieces from radioactive water systems associated with the nuclear power plant. You would change out these sort of filters fairly routinely, and none of that stuff is that long-lived. It's a lot more it's more reactive than low-level waste, but not nearly as reactive as the high-level waste. So usually those are left on site until a lot of it just decays away, and then you can either just dispose of it with regular trash once it's not radioactive anymore, but some of the more long-lived stuff does need to be sent into a waste repository where it accumulates, but again, by volume, not nearly as much. This is, and by long enough, we're talking on the order of days rather than years. Doesn't have anything like that either. This wasn't a big, you didn't have like a liquid waste processing system or a reactor coolant system, reactor coolant purification system. That's still a lot of intermediate level stuff is still nuclear plant stuff. What he does have is low level waste. And this is 90% by volume. Stuff with gloves being contaminated with radioactive material, protective clothing, all of that sort of stuff. And that's fairly frequent. A lot of that can be treated just by doing laundry. There are special big washing machines and dryers, industrial sized ones, at a nuclear plant in a radiological controlled area that can take care of that sort of thing. That stuff is highly treatable, highly able to be taken care of. It's recyclable. So this is what he would be considered low-level waste. And whether or not he would need to send it to another site to have it taken care of, a lot of that just depends on how much of it he has, both in terms of volume and in terms of activity. Now, uranium, unfortunately, one of the things about uranium is it's a very long half-life, so the whole waiting to decay away thing is less of a thing, because uranium 238, we're talking billions of years, and 235, we're talking millions of years. So that option of waiting for it to decay away isn't going to be a thing. So the likely scenario would be to have it, he's probably just going to need to send it off somewhere to a low-level waste repository. Let's see what he does next.
There also might be a couple things missing here, and it's because I cleaned them while the project
was going on. Not sure how much he has.
To deal with all this paper and gloves, there really wasn't much that I could do. I probably could have tried to chemically recover the uranium from them, but it just wasn't worth it.
The key thing is don't contaminate other things with them. So yeah, what he's showing on the screen is exactly what you need to do. Just put them in little baggies to make sure you don't have, I recall in that video, he had a lot of particulate sort of contamination. So you just don't want it to go, everywhere, because if you have something that you pick it up with, so the gloves he's using, that's all going to be considered radioactive waste now. Like, again, very little activity, and the only really thing is contamination spread that you have to be concerned about. But you touch waste, the thing you touched it with is waste. And that actually isn't limited to just radioactive waste. That's any sort of hazardous material training, just the basic OSHA stuff says stuff like that. And one of the first things about nuclear waste or any hazardous waste is do not mix it with the non-hazardous waste, because then, lo and behold, you got more hazardous waste, and in this case, you got more nuclear waste. That's not to say it's a sufficient enough quantity that it's a health concern. It's just you need to keep it sorted to minimize the overall volume of waste.
So instead, I just threw it all into a bag. Then with everything taken
keep it in the same bag.
I rinsed the bowl in the container with some water, and I wiped it down a few times. This got rid of any uranium that might still be there, and I threw all this paper towel into the same waste bag.
Good job.
To clean the rest of the stuff, it was pretty much the same thing, and I just shot it with a bunch of water and wiped it down. After that, I dumped all the water in the beaker into the bowl, and I took out the stir bar that was in there. This bowl now had all the water from the original reaction and all the washings from the cleanup. Most of it was just water though, so I decided to get rid of it by just letting it evaporate. I don't remember how long it took, but all the water did eventually disappear, and I was left with this crust at the bottom. I usually do my projects in parts, so this was all done before I even started making the glass. When I did finally get around to making it though, I had to grind the uranium, and this left me with some more contaminated glassware. To clean this, I wasn't able to just wipe it all off, and I had to convert the insoluble sodium diuranate back into uranyl nitrate. I did this by adding a small amount of concentrated nitric acid, and then I diluted it with a lot of water. I then added a bit more acid, and I let it sit for about an hour to make sure that it all reacted. After that, when it looked good, I poured it all into the bowl from before. I washed it thoroughly with a lot more water, and I also washed a glass funnel, and some pipettes, and some spatulas. All of this water was again evaporated by just letting it sit there, and this was the final waste. I think most of it was actually sea light, which was all that white stuff, and I used it as a filter when making the sodium diuranate. There probably was a small amount of sodium diuranate in there though, and there was definitely some uranyl nitrate. To test how radioactive it was, I used my Geiger counter.
There you go.
And it really wasn't that bad. Just for fun, I then shot a black light at it, and it did end up fluorescing because of the uranyl nitrate that was there. After this, I wiped down the entire room, and I made sure that there were no residues left anywhere. And in the end, this was all the waste that I was left with. A few bags of dirty paper and gloves, and a bowl of minorly radioactive crust.
It's good. I have to say, I like the way he sorted it out, and I also just get mesmerized watching his videos just in general of something about the combination of soothing voice to the very precise way he handles all of his materials and methodically cleans. It's actually quite relaxing watching these videos. But yeah, the big thing is sort it, package it, and keep it separate from everything that isn't radioactive just to not contaminate anything. Looks like he's doing all the right things.
All of this was then put into a lead-lined cabinet that I used to store all my radioactive stuff.
That's a lead-lined cabinet. That's awesome.
It's probably just going to sit there indefinitely, but eventually, I do plan to pay someone to deal with it properly.
One of the items that we have in the radiological controlled area when you leave it is lead-lined counters to check for contamination, and that's to check for tools like your gloves, your clipboard, if you happen to be carrying around a procedure with you. In some cases, your hard hats, but they usually use a different sort of detector for that, just to make sure your tools are cleaned when you leave the radiological controlled area and then enter a part of the plant that is not radiological controlled because there's essentially no risk of radioactive contamination. Note that our health physics / radiation protection technicians do have the ability to extend the range of the normal radiological controlled areas if for whatever reason there were to be some sort of contamination, or this would be a crazy accident scenario. I've never encountered one when I worked. They control the boundaries of what should be monitored and what shouldn't be. And just if you're relatively new to my channel, when I say radiological controlled area, I'm just referring to a monitored area, not an area where you're necessarily going to be right next to radioactive material or you have a risk of being contaminated. That's not necessarily the case at all. This is just an area where where entry is restricted to personnel that have received radiological training, and access is controlled. You have to have a briefing with these people before you go in and before you leave. Note that there are even local area radiation monitors in areas where that is not in the radiological controlled area, just in case an accident like that were to occur. We have all kinds of redundant systems to keep people at the plant safe and monitored. That's ultimately one of the fundamental goals about operating a nuclear power plant, is obviously to generate electricity, but very much safety over production mindset, and to keep everyone safe from radioisotopes.
Besides all this stuff that I just showed you, I did have some other waste, which was all the broken uranium glass and the things that I used to melt it in. As the glass, it was probably okay to just throw this all in the garbage.
Probably okay, depends on local laws and amount of uranium in the glass. I think it's best to keep it or dispose of it properly, though, even if it's technically legal or okay to throw out. So yeah, there are numbers associated with, I mentioned earlier about the amount of the material by volume and the amount of material by activity. Uranium is one of those things that is going to be around for a while, so the whole decay thing isn't really a factor. You might as well just assume it's stable because it has such a long half-life. The conservative action would be, regardless of how much of the material you have, to just cluster it all together, put it in bags, and the fact that he has a lead-lined cabinet is awesome. And just send it off to a low-level red waste site.
But I didn't really feel comfortable doing that. I also thought these pieces looked pretty cool, so instead, I just decided to keep everything. That was basically it, though, and in terms of cleanups, it wasn't anything too crazy. In a lot of the other cleanups, I had the ability to mess around, which was what made it fun, but there wasn't much room
Took a drill to it.
I made an exception for this one because so many people asked.
You don't want to get radioactive material kicked up.
Cleanups for things that I personally had a lot of fun doing or thought were particularly interesting. But anyway, that's about it for cleanups.
That was really cool to see. I'm glad he shared it with everyone, that what he did with handling radioactive waste. That's something that I don't think comes up really often on this platform, but it really speaks to his professionalism and how he handles the cleanup, and him following all the right protocol with how to safely dispose of radioactive waste, even in an amount that isn't really going to threaten anyone, but he's showing the conservative action. Lead-lined cabinet, sort it, and sending it off. That's really good to see. Thank you very much for watching. I'll see you next time.